Hello everyone, welcome back to our channel. Today we are going to learn about artificial intelligence and machine learning lecture series. In our previous videos we learned two important search algorithms, breadth first search and depth first search, that is BFS and DFS. If you have not watched those videos, I highly recommend to watch them first because today's topic builds on those concepts. Today we are going to learn another powerful search algorithm called Iterative Deepening Depth-First Search, commonly known as IDDFS. IDDFS is considered one of the most useful ununiformed search algorithms because it combines the advantages of both BFS and DFS. By the end of this lecture, you will understand what is IDDFS, why it is needed, how it works, step-by-step iteration, backtracking, advantages and applications. So let's begin. Before understanding IDDFS, let's ask an important question. We already know BFS, we also know DFS, then why we go for another search algorithm? Let us compare them. Breadth first search. BFS explores nodes level by level. Its biggest advantage is that it always finds the shortest path in an unweighted graph. However, BFS has one major drawback. It stores every node at every level. As the search tree grows, memory usage becomes extremely high. Now let's consider DFS. DFS follows one branch completely before exploring another. It requires very little memory because it stores only the current path. But DFS also has a disadvantage. Suppose the goal is located at depth 2 instead of finding it quickly. DFS may continue exploring another branch until depth is 20 or even deeper. This wasting time. So ideally we need an algorithm that useless memory like DFS and still find the shortest path, shortest solution like BFS. That algorithm is called Iterative Deepening Depth-First Search, that is IDDFS. Now let's understand what is IDDFS actually. It performs depth limited DFS repeatedly. Instead of searching the entire tree at once, it searches only up to a particular depth initially. The depth limit is 0 if the goal is not found. The depth limit becomes 1 again if the search starts from the root if still not found. The depth limit becomes 2, then 3 and 4. This process continues until the goal node is found. You can compare this the clipping a staircase. First you check only the first step. If the required object is not there, you check the second step, then third. Eventually you reach the correct step. That is exactly how IDDFS works. It is a combination benefits of DFS and BFS, and searches to a limited depth, ensures both completeness and optimality, ensures exploration of all nodes at the depth before going to deeper. Now let's discuss the important features of IDDFS. First, the search strategy is depth limited DFS with increasing depth internally. It uses a stack just like DFS. Since only one path is stored, memory usage remains very low. Unlike DFS, IDDFS is complete. This means if a solution exists, it guaranteed to find it for unweighted graphs. IDDFS is also optimal. It always finds the shortest solution because every depth level is completely explored before moving deeper. Therefore, IDDFS combines the memory efficiency of DFS and completeness of BFS. Now let us discuss the advantages of IDDFS. First, it combines the strengths of BFS and DFS. Second one, it requires very little memory and it always finds the shortest solution in the unweighted graphs, and it is complete, and it is extremely useful when the depth of the goal node is unknown. Okay, it first searches up to depth 0, then depth 1 and depth 2, and continuously increasing the depth limit until the goal node is found. This approach uses the low memory of DFS while maintaining the completeness and optimality of BFS. Let us understand the working of the algorithm. Assume A is the root node and goal node is somewhere deeper inside the tree, that is I. Instead of immediately searching deep branches, IDDFS proceeds gradually. First, we fix level 0, that means depth limit is 0, that is iteration is 0. Only one node A is only visited. Okay, now it is checked goal node is found or not. No, goal node is not found. So next depth level, that means iteration level is increased. Now iteration level I is equal to 1. Now DFS explores one level deeper. Now visited the nodes A, B, C, D. Okay. Now question will be asked, goal node found? No, there is still no. Okay. Next, increase the depth limit again. Now going to increase iteration 2. Depth limit is 2. First, now observation iteration 2, the search starts from A. Okay, moves to B, then E. E has no children nodes, so here backtracking occurs. Okay, what is backtracking means I will explain later. The algorithm returns to B. Okay, now it explores F, then F. Again there is no children for F. Now also it will backtracking to A, and then start from A and visit C and then G. Now also there is no child for G, so it will take backtracking, then move to D, then H, and finally visit I. Suppose I is our goal node, immediately the search stops. Okay, final traversal order becomes A, B, E, F, G, D, H, I. Okay, This example clearly shows how IDDFS gradually increases its search depth until goal node is reached. Why does not IDDFS restart from the root? At every iteration, the algorithm increases the depth limit, so it must restart from the root because nodes that we previously beyond the depth limit now we explored. For example, iteration 0, depth limit is 0. Now visited node is only A. Okay, next iteration 1, depth limit is 1. Now visited nodes are A, B, C, D. Okay, finally iteration 2, depth limit is 2. Now visited A, B, E, F, C, G, D, H, I. One of the important concepts in IDDFS is backtracking. Backtracking simply means returning to the previous node whenever no further child nodes are available. For example, suppose the algorithm moves A to B, B to E. Now, if E has no children nodes, the search return to B. Okay, then it exports F. Once F is completed, it again return to A. This process continues until every possible branch within the current depth limit has been explored. This is called backtracking. Example, A to B, B to E, no more children are found. It will take backtracking to B and then F, and found there is no children found, so it will take also backtracking to A, then it explore C and then D. Okay. Why use IDDFS? IDDFS is widely used in many artificial intelligence applications. Instead of searching the whole tree with the DFS and IDDFS checks is it at depth 0, if not check in depth 1, and if not check depth 2. Continue until the goal is found. IDDFS uses in robot navigation and puzzle solving and chess games and game tree searches, path planning and GPS route exploration, automated planning, state space search, artificial intelligence problem solving. Whenever the solution depth is unknown and memory is limited, IDDFS becomes one of the best choice. Thank you for watching.